Right, so we've got all our pieces ready down here to go. But now we need to work on the points. So I'm going to come to back to the top here and drop a wrangle. And let's move this over to the side. We're going to be starting a new kind of stream of data coming down the side. Okay, so I'm going to come here and I'm on the 5th frame because I want to work on the velocity values here. And this is a vector at the moment. So what I want to do basically is just make a selection of a certain speed of points. So to actually get that speed, we need to convert the vector into something that's easier to work with and to a float value, right? So I'm going to call it float speed is the length of the velocity. Okay, so if we won't be able to see this now, but actually if I just turn this into an attribute, it will be global and we'll be able to see it in the geometry spreadsheet here. So you can see that we've got something a bit easier to work with now, so we can, you know, make a selection of velocities between, I don't know, 10 and 20 or whatever. Okay, so so we're starting off with that. So the length will give us the magnitude of this vector, right? And let's make an if statement. So if the we'll change this. Yeah, well, no, we'll leave it at global attributes. That's fine. If the speed is more than, and we'll make a channel a float, and we'll call it let's call it max. I'll call it max speed, or let's see, or the speed is less than channel F min speed. Then we're going to remove points on the first input, and we're going to remove the point that we're currently iterating on. This point, and that's the end of our expression. Okay, so we'll get an error there at the beginning because I've forgotten a bracket here. There we go. So we're getting something straight away. All of these have a velocity of 0. So we need to click this to make our channels here. We'll get them there. Okay, and then hopefully as I raise this, you can see we're getting a higher value here for the max speed. And then if I raise the min speed, you can see we're making a selection now. Okay, so what this is saying is if the, Control Z, I don't know what I did there. If the speed, this speed is higher than this value, or, so these two lines mean or, lower than this value, then delete. And we only need to delete the points because we're using we're still packed geometry. So, you know, each piece is represented by 1 point. So I'm going to raise this to a bit higher, to 17, and then the minimum to 3. I think it wants. Okay, so that gives us a nice chunk. So I don't want to be emitting from the little tiny pieces that go above. So if I raise this even higher, you can see we get, maybe if I go a bit later, get pieces kind of up there. So I want to kind of bring that down a bit because I don't want to have kind of streams of debris, you know, like lines, vertical kind of columns following the faster moving pieces. So I want to bring it down a bit to these bigger chunks that are lower down here. Okay, so maybe we'll give that a name. Let's say cull by speed for that. Okay, now I'm going to unpack this. And we're going to want to keep the velocity, so because we want to pass the velocity onto the debris pieces so that they follow in the direction, otherwise they'll just be emitted and then drop to the ground. Now I want to delete the outside, so we should have an outside group, this one. Okay, so that means we'll emit from the kind of edges, the fractured parts, not from the surface, which makes more sense. Let's do delete outside, name that. Okay, now I'm going to peak this a little bit, because when the points are created, I want them to be a little bit away from the surface, so that we got less chance of debris pieces being inside the geometry. It might be, we might have a few that go inside, but this will help us a bit. So just a tiny bit. See, they kind of all swell up a bit just to push them away. Now we're going to scatter our points onto this. Okay, so I'm going to have a total count of 20,000. Okay, so each frame will have 20,000 new pieces. Well, possibly. We're going to actually delete a few down again. I'm going to get rid of the relaxer iterations, so that it's just as random as possible. Okay, now I want to, just to be sure, because we still might have some points inside of the collision geometry, which is the original simulation. Okay, I'm going to make a group and use this. We're going to have to unpack it to make this group. We don't need to pass any attributes across. Come here, make this group, be on points. Let's just call it delete me, just to be sure as well. Well, after I'm done with this, I'm going to delete this speed attribute and this group, because we don't need them afterwards. Let's go there, and then we're going to delete by bounding region, bounding object, and there we go. Okay, so you can see where we're selecting quite a few there. So if I go to drop a delete now and delete that actual group that we just made. Okay, so you can see the difference there. We've got 11,000, so we deleted 9,000 points there, quite a few. You can see in the group there's about 9,000. Okay, so these are all points which were inside the collision geometry. So there's no point simulating them, because they're going to be they'll most likely be trapped inside called pieces. Got that? Cool. Okay, so now we're going to copy these pieces onto these points, and obviously we need a way of randomizing that. Yeah, so I'm going to drop a attribute randomize, and I'm going to make an attribute called variant. Sorry. Okay, it's going to be it's going to make a float for us, but eventually we'll change it into an integer. We're going to use an uniform discrete so that we have whole numbers, and we have 7 points here. So I want values from 1 to 7. Okay, so if we take a look at that now and find our variant, you can see we got values from 1 to 7 randomly distributed over our points. And take note, we've picked up that velocity as well onto our scattered points. Just naturally, the scatter picks up the velocity from the piece. Okay, and as I said, we want this variant to be an integer. Now it's a float. So if we use an attribute cast, okay, and change that. So this is variant, and we want it to be a 32-bit integer, which is that. Perfect. Okay, so you can see we don't have that floating point now. Give it its name, variant. Okay. Variant to int. Cool. Let's see. So now we need the equivalent. We need that variant attribute on these points as well, right? So I'm going to drop an attribute wrangle on this side, on our points, on our actual pieces. Okay, and give it that same I@, variant is, and then I'm just going to use the point number, pt_num, and because the point number starts from 0, we just add 1, and that will give us a variant of 1 to 7. So we got 1 to 7 on here and 1 to 7 on here, and we can use them to match up one piece for each point. Okay, so now we drop a copy to points. Okay, and then you can see this piece attribute, which uses this variant. You can call this whatever you want, but I'm just using variant because it's there. Connect that up, and then if we visualize that, we'll see we got loads of pieces. They're obviously way too big at the moment. Let me turn this lighting off, and but it's working. We got a variation of different pieces scattered onto that. Okay, so we can use p-scale to affect the size of these. Okay, let me just call this create variant. Great variant on that. Cool. So yeah, we want to randomize the p-scale as well. Okay, so I'm going to drop an attribute randomize here. So p-scale is a global attribute which affects the size of instanced objects or particles. So it's something you will commonly use if you haven't already. Okay, so we just call it p-scale, and this is understood by the copy to points. Even probably now with this, it will still have an effect. Yeah, you see, even with that. So just by generating the attributes and giving me values between 0 and 1, it's making a difference. So I'm going to make a ramp, so a custom ramp. Let's turn off the visualizer because that's going to take a bit of time. And let's see. So I want the biggest size to be 0.5. Okay, and I want a bit of a ramp here. So this point I'm going to set at 0.8, the value of 0.1. Okay, and I don't want it to go to 0. I don't want points of size, you know, without any size, otherwise there's no point simulating it. So I'm just going to give them a very small scale of 0.01. If we move this down, you can kind of see what we're getting. I'm going to get rid of this kind of curve as well, just set it to linear on all of them. Linear there. Okay, so we get a nice straight line. Now if you visualize that, we'll get much more variation in our pieces. Okay, now it seems to me some of these pieces might be a bit big, and to make a comparison, let's see how they look with the rest of the simulation. I'm just going to grab these points, just merge this together just temporarily to visualize this. You can see some of the pieces are kind of as big as, you know, the original bits. So let's drop these down. So I'm going to come into my, let's put p-scale here, p-scale, and yeah, I'm going to drop this one down. Let's do it to 0.3. Maybe this one, let's do 0.05. something like that. There we go. So they're much smaller now. Great. And then one more thing to do it's not essential because the pieces are so small, but just to randomize it even more is I'm going to randomize the normals, which will randomize the orientation. So just a quick way of randomizing the orientation of our pieces. Okay, so I'm going to set this to inside sphere, and we need 4 dimensions for this to work. Okay, so if we zoom in, I turn that off, you can see the rotations changing there. With it off, you probably can't notice, but if you have two pieces the same, they'll be rotated in the same way. Okay, and then changes to normal. Cool. And that's our pieces ready to go.